Yeah, please go ahead. Yeah, it started. Go ahead,
Okay.
Ross.
Okay. So today we are going to synthesize 2-phenyl indole. So here, if you see the structure, so this is the nitrogen. So this is the position 1, and so next to nitrogen is position 2, and there is a phenyl substitution at position 2 of indole. So this fused bicyclic system is called indole. So that's why this is called 2-phenyl indole. So actually, this indole system is very, very important biologically. So we can found this system in many natural products, including plants and animal. And most important part is indole is a part of an amino acid side chain, tryptophan. And so indole has a lot of functions as a medicine. This is acts as a neurotransmitter, works in brain, it's work in kidney, in liver. So this is very important for human being. And so synthesis of indole will do, but today's experiment is actually very important in that sense that today we will do a consecutive reaction. That means first we will do one reaction, and the product we obtain from the first reaction we will do for the second reaction. So today's experiment is a multi-step synthesis, and for this kind of multi-step synthesis, you have to be very careful because you will use the product of the first synthesis as the starting material for the second synthesis. So if you got less product from the first synthesis, obviously you are going to stop with very low yield. And so that is the thing. And second thing is that will for today's experiment, it is a very, very old method of synthesis of indole. And you will be surprised to know that when that experiment was first developed, there was no analytical techniques at all, and so people don't know how they got to that point, but they get the product and they characterize the product as per the method available at that time, and they were correct. Okay. So what we have to do, we have that equipment for today's experiments is obviously the heater, stirrer, balance, water bath, whatever it is. Reagents we need phenyl hydrazine, acetophenol, ethanol, glacial acetic acid, hydrochloric acid, rectified spirit, phosphoric acid, distilled water, decolorizing charcoal. Probably we don't need it. If there is lot of color, we can use that. Anyway, and glass apparatus is also simple. So beaker, glass rod, funnel, measuring cylinder, conical flask, etc. So what we are going to do, so we'll dissolve uh, phenyl hydrazine and acetophenone in ethanol in a 100 ml beaker. So that is very important. So you have to dissolve it completely. 2.2 gram of acetophenone in 60 ml ethanol in a 100 ml beaker, and then add 1.8 gram phenyl hydrazine and 5 drops of glacial acetic acid to this solution. Okay. And so this will react, you know the reaction already, you are going through that organic mechanism classes, organic synthesis classes, and so we'll prepare this first intermediate. Okay, and for that purpose we need to gently warm the reaction mixture on a boiling water bath. So be careful, it is not direct heating on a heating mantle. So sometimes that heating mantle we cannot control the temperature, and it may char the product. So from the beginning you will get a very dark color material. So we will heat it gently on a water bath. So it's a boiling water, vapor is coming out, and on that vapor we will heat it. So on a boiling water bath for 60 minutes, and start well. And so we'll start it with a glass rod occasionally, And so what exactly will happen? So both the reactant as well as the products are highly soluble in ethanol. So with heating, we will evaporate the ethanol, the reaction will take place, and finally, once the ethanol is evaporated, your product will solidify. And so we'll cool and allow the white precipitate to settle down. So the product of this white precipitate we will collect, filter, and we'll wash it and with dilute hydrochloric acid and followed by cold rectified spirit. So first we will wash with dilute hydrochloric acid. So if there is any unreacted amine that will react with hydrochloric acid and that will go up from the product, and then we'll wash it with cold rectified spirit. So if there is some unreacted acetophenone that will dissolve in rectified spirit and that will also go. Okay, so once our phenylhydrazone solid we got this material, we'll place that 2.8 gram of that crude phenylhydrazone in 250 ml beaker. So we'll do this reaction in a beaker, not in a conical flask, in a 250 ml beaker, and we'll place 18 gram of polyphosphoric acid. So polyphosphoric acid is very viscous material. It's also called syrupy phosphoric acid. It's very difficult to transfer. So we'll use the glass rod to transfer 18 gram of polyphosphoric acid and in that beaker. And we'll heat on boiling water bath. So again, we'll place that beaker on water bath and on boiling water and continue heating for 10 minutes. And be careful, this is an
Hello. Hello, guys. Am I there?
Yes, sir.
But okay. Professor Haldar got disconnected.
suspecting cancer causing reagent. So if you have any question.
This is the in between. You were offline, but I
Oh,
think you
there
were
is a
just mentioning, yeah,
power
mentioning
cut.
about the last part of
Mhm.
the.
Okay, so actually phenylhydrazine is a suspected agent for cancer. So that's you have to be careful when you are handling phenylhydrazine. Yeah, so if there is any question, please. So if not, Shumon will show you the reaction mechanism and discuss the points. Yes, Shumon.
Yes. All right. Is the board visible?
Not yet.
Yeah. It's okay.
Yes, yes.
All right. So let's come to the mechanism part. And as Professor Haldar already mentioned, it's basically a two-step procedure. First step is not, it's quite simple, it's just a condensation reaction, and the main mechanistic importance will come in the second step. So we'll just draw the reagents here, and then we'll obviously discuss the second step in more details. So what's the reagents here? So we are taking this phenylhydrazine, which is PHNH NH2 plus acetophenone, phenyl COCH3. And in presence of this little bit of glacial acetic acid, so that means it's just a source of mild acid. Okay? So there should be the catalyst, only few drops you need to add in ethanol solvent. So once you do that and heat it up, so what happens? So it's just some protonation will happen here, and then amine will attack. This amine will attack here, and just a condensation reaction will take place. Ah, so I'm not going into details. It's quite obvious. I know you guys already know this. Amine here, so minus water will go out, and it will form basically imine, but it's a special kind of imine because imine means there is a C double bond end is imine. But when that imine, the nitrogen is connected with another nitrogen, extra nitrogen is there, then it's called hydrazone. Okay, this is hydrazine, and this is the product we call hydrazone. Let me draw that. So this is basically imine, right? When there is a nitrogen, and when there is another extra nitrogen here, then it's called hydrazone. So after first step, so we'll get this one. So this is quite simple method to reach up to here. The second step is the most important and interesting part, and it's a part of a classical synthesis. That's called Fischer-Indole synthesis. And it's good that you already learned this physical organic chemistry, and the pericyclic reactions was a part of it in last semester. I really believe that you remember that. And you will see today one up to now you just read pericyclic reaction theoretically, and now in today's video you will see a pericyclic reaction is really happening inside the lab. So the second step is a part of a pericyclic reaction. So let us just trace the structure so that we can really show the mechanism. What I will do, I will just stretch it the phenyl ring first here. That is what we need. This is the part of the hydrazine, and then it comes the hydrazone part, and here one H is here. So I just redraw the structure here, nothing else. So this is the starting material for the second step, and we are adding this viscous phosphoric acid, this polyphosphoric acid, which is a quite strong acid. So plenty of protons are around. So this nitrogen will catch up one proton. And this will become positive. And this is positive, will promote a tautomerization. Will promote this tautomerization from this intermediate. H, double bond here, and phenyl group here. Okay. So now this is a perfect intermediate for the pericyclic reaction. Okay, how? So in pericyclic, probably have learned a lot of things. Any pericyclic reaction, whenever I ask in an interview or viva to a student, there's a Diels-Alder reaction. I know that Diels-Alder probably one of the most popular reaction. That is the 4+2 cycloaddition reaction. But as you know, there are many other kind of pericyclic reactions, and among others, sigmatropic reagents are also very one of the very important variety of pericyclic reactions. And here, exactly that sigmatropic reaction is happening. Okay, so let me point out where it's happening actually. So sigmatropic also there are, sigmatropic means where one sigma bond will break and new sigma bond will form, and in that process a few pi bonds will also get rearranged. Okay, so that's the sigmatropic reaction. And in sigmatropic reaction also, there are depending on the structure of the molecule and where exactly the sigma bond is breaking and where exactly the sigma bond is forming. Depending on that, the pericyclic reactions are designated with a number. Okay, so sometimes it's 3 sigma tropic or 2 3 sigma tropic like this. Okay? So how the number is coming? Let me first draw the arrows so that later on we'll give the number. So here the sigma tropic reaction will happen like this sigma bond here, it will break. This guy will break, and then there will be a new sigma bond here, like this. This guy will come here, this will go there to make a new sigma bond, and this will come here. So in this process, you see this sigma bond is breaking, one new is forming, and these double bonds are getting rearranged. Okay. Let me first draw the intermediate after the sigma tropic reaction here, like this. So it becomes double bond nitrogen. H is there. This is the new bond, new sigma bond, which is formed, carbon carbon bond, and here also it should be this NH, and then it is like this. This is the situation. Now let me give the numbers. For number, let me take a different color so that you can understand better. The number goes like this. You see, the rule is, I know you were, just to recapitulate, I'm sure probably Pradeep sir taught you these things. This sigma bond, where the sigma bond is actually breaking, you have to start numbering from there. So this is number 1, this is number 2, and we have to end up where the sigma bond is forming. Okay, 3, 1, 2, 3, and this side also have to follow the same. Okay, so this terminal also 1, 2, 3. Okay, so that means this is, and we have to number this. Sigmatopic reactions are always showed at in a third bracket like this. And so the rule is, I repeat, where the bond is breaking sigma bond, we have to start the number from there and go up to the point where the sigma bond is forming in both the sides. Okay? So we have done this and we have found this 1, 2, 3, 1, 2, 3. So, and but we actually have to mention the number or the final numbers, okay, where the sigma bond is forming. So it's called 3, 3 sigmatropic reaction. Sigmatropic reaction. 3, 3 sigmatropic. Okay. So let us continue. We got this product. Is just after that. This is the most important part, the sigmatropic reaction. And after that, just regular routine reactions. So the proton is here. One H was here, right? So this guy in 3 position there was one H. We need to show it now, just to get the aromaticity. Because during this reaction, the aromaticity of this benzene ring gets broken. So it's trying to regain just to by deprotonation here, or rather to say tautomerization. Better to say it's a tautomerization step. Let's get this. This becomes NH2, and this benzene ring gets back the aromaticity. This becomes NH2, and here situation is like this. And phenyl is here, H is here. Okay. So the last step here, like this lone pair of nitrogen will attack in this imine. Okay, imine here, because the carbon nitrogen double bond imine, and this will take one proton here. Sorry, the space is small, that's why probably is getting a little bit congested, but I hope you are getting it. This ring is completed already. So once this attack is happening, count it how many members ring is forming. 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. 5-membered ring is forming. So let us draw the 5-membered ring here. Okay. And so phenyl is here, and this will become NH2. And one of the, during this process, one of this nitrogen, hydrogen from the nitrogen will also get lost because it's donating lone pair. So it will become plus, so it will just release one proton. We can just show in one step. That's also is becoming NH. Right. And this is the thing. Last step, And now the indole ring also got the flavor that it can also become an aromatic compound. So that's why this proton will get lost, and this thing also take a proton and it will release as ammonia. So one molecule of ammonia will come out from the reaction mixture, and this is the ultimate product. NH here and phenyl, 2-phenyl indole. So that's the ultimate product. Okay. So just to repeat it, first step is quite simple. Just is condensation reaction to form the hydrazone, and then with the hydrazone, it's the actual key step with presence of acid, little bit of heating, will first automerize and then form this intermediate here, and then the key step, the 3,3 sigma-trophic reaction to form this, and then routine re-aromatization and attack their release of ammonia, and we get the indole. So it's a beautiful synthesis, starting from very cheap materials. Phenyl hydrazine is also cheap, acetophenone cheap, and this, as Professor Haller already mentioned, this indole code structure is really valuable. So someone, if and the thing is, this classical method so old, this Fischer indole synthesis, but still to date people are using this, and it's one of the most popular and most used method. So if you can make something which is more useful or more efficient than this, you can make a lot of money, I can assure you. That's the thing. So if you have any question, you may ask me. Students, you can type. If not, then I can start the video. Rosita? Okay.
Yes, please.
All right. So is it visible now?
Yes.
Let me increase the volume, otherwise I've seen that. And see, she's taking really protection because phenyl hydrazine is toxic. So the lab coat and gloves is mandatory, and of course she's taking extra protection because of COVID. Okay, welcome to this new experiment for the synthesis of indole. And today Nidhi is here, Nidhi Kumari, who will help us in doing the experiment and will show you how to prepare phenyl hydrazine and acetophenone using phenyl hydrazine acetophenone, how to prepare the indole. Okay, let's proceed. As instructed, we're going to do the synthesis of indole today, and there are two-step process. First step is the preparation of hydrazone, and afterwards the rearrangement to make the indole. For the first step, we need acetophenone and the phenyl hydrazine, and we are now going to add the ethanol, the solvent here. 30 milliliter of ethanol we have taken. Now we are going to take the acetophenone inside the ethanol solution. Required amount is 1 gram. So, both are liquid, so it's got easily dissolved. Now got the solution of acetophenone in ethanol. Now the homogeneous mixture. So the second reactant is coming in, the phenyl hydrazine. But the density is almost 1.1. We need 0.9 grams. It's coming around 0.8 milliliter of phenyl hydrazine. The solution of acetophenone. So after adding these two solutions, all the liquids is now soluble, and we need some catalyst, the acetic acid, promote this reaction as as per the instruction. We need only few drops of acetic acid to promote The mechanism already I discussed this thing. Adding few drops of acetic acid. The solution, you see, we got a nice yellow color of the reaction mixture, but still no product yet. For this, we need to pick it up the water bath. So we're going there for the heating. We have poured the reaction mixture here in the water bath and heating it. So for next 60 minutes, we heat it up, and with some occasional stirring if required. If you see any solid, stir it. After 60 minutes, we cool it down, and then we'll show the product formation. For 1 hour of heating, we cooled it down, and you can see the volume we reduced a bit so that the precipitate can come. And I'll ask Nidhi to promote the precipitation of crystallization by scratching. Yes, yes. See here, sometimes this mechanical energy is useful to get the nice crystals or to promote the precipitation. You can say mechanical energy here in the scratches, from the scratches promotes the precipitation. You can see from this scratching point, more and more precipitates are coming. Yes, yes. Right. Yes. So we'll continue this thing and allow all the products to precipitate out from the solution. Then we go for the filtration. Yeah, this is a characteristic of hydrazone. Most of the hydrazone, so this scratching, so probably it's increase the local concentration somehow, and then this collision between molecules probably, and precipitate means the same molecules are coming together and going out of the solvent, right? So normally when something is soluble in solution means it's inside solvent cage, right? So there are amount of solvent molecules compared to the substrate is much higher. So it's surrounded all the molecules by several solvent molecules. And during the scratching, it helps to break these cages, and then two hydrogen molecules are coming closer and then precipitate out. So initially, in this particular reaction, it was no precipitate even after the reduction of the thing. When we started sketching, and then precipitation started. And sometimes this crystallization or precipitation, the thing is, initiation takes some time, and once it's initiate, it acts like an auto catalyst. Okay, so some amount got solid, and then it's bringing other same molecules for taking out from the solution. Okay? And then scratching also helps. So it's also this technique people take. Suppose crystallization, and sometimes it happens there is no crystal. So you reduce the solution, then you are not getting crystal. You cooled it down, still no crystal. So this technique also people use. They take, the compound, or this is the what compound is this, and then you take from previous batch or something, where suppose you are making it for the second time or third time, you had something little amount from the previous batches. You take little solid and add there in the solution, and then it initiates the crystallization. Okay, so the above one crystal, then is a layer of crystals, and then it's a series of crystallization, and you get nice crystals of this. Okay, so we are doing the filtration here, routine filtration. Let us continue. After the precipitation, we are doing as usual filtration, standard filtration, and as mentioned in the instruction, we are washing it with cold normal HCl just to remove the unreacted hydrazines. The hydrazines will just get dissolved, the normal HCl, and then go away. This part, the hydrazone part, will remain as it is. Very nice precipitates of this hydrazone product. Maybe we'll check the melting point here, and also we'll take some part of it and proceed for the next step. So here we got relatively good puritic product. It was not very much colored, so that's why we did not use this active charcoal. So sometimes, it will get very colored, so that means some impurity is there. So you use some active charcoal to remove. Ideally, this product should be white. So you can see it's a little bit dirty white, but still it was good enough to proceed for the next step. So we did not use the charcoal.
We are proceeding for the second step. For that, we have actually reduced the scale and taken 0.5 gram of phenyl hydrazole in a beaker. And now we are adding the phosphoric acid. Here, actually, you see the phosphoric acid is a very dense liquid. You can't really drop it out. So we are, yeah, just as that's good enough. So we have taken just by a glass rod and then roughly 4.8 gram because we are using a reduced scale. So that's why we don't need 9 gram, 4.8 gram. They have taken here, and you see here. I asked Nidhi to just make a star here, take it out from the balance. Yeah, starring here. So you get a viscous kind of reaction mixture. See here, but for this Fischer indole synthesis rearrangement to take place, we need heating. We'll proceed towards the oil, this boiling water bath here. Yes, this one for heating for around 10 to 15 minutes, and then we'll show you the progress. Thing here, and you can see this viscous liquid now is turning into a transparent solution, and the color is also getting a little bit darker, more darker. So we'll just continue for 10 to 15 minutes and then take it out and do the rest. You have taken it out from the reaction mixture. Now you add the reaction mixture, we need to add the cold water. Adding the cold water. Here, oh, precipitate is coming out, and the whole amount of water. Continue stirring. Precipitate. Nice white precipitate of indole came out. You can see color changed completely now. It's milky white precipitate of indole. You can see it's getting settled down here. Yeah, you can see. Maybe star a little bit. Yeah, you can see. Slowly, slowly, star slowly. Yeah, you can see the precipitate of the indole. We'll just wait for a few more minutes, and then, as usual, filter it. And then we'll do the TLC to show you how to characterize or differentiate whether the reaction is complete or not. Filtration here, as usual, very milky white reaction mixture, giving very nice product of filtration. Fine particles there, that's why probably the filtration is a bit slow, but we'll just wait for a few more minutes. Sucks all the water. You can already see very nice product precipitate is coming out. Yes. Almost getting dry. Product form is very white in color. All right, so we'll just wait for a few more minutes so that all the water goes out from here, then or from the to the in layer chromatography or TLC. For that, we need this TLC plate and the TLC chamber here with some solution here. You can see here, which is the eluent here. And as we have already explained separately, that we need to spot the reactants also. This is a solution of acetophenone, the solution of phenyl hydrazine. This is the final reaction mixture product where we expect to have the this indole product, and here is the phenyl hydrazine. Sorry, the phenyl hydrazone, that the intermediate product
So
of the
yeah,
last step.
yeah.
So this
Actually, I will pause here, and then I forgot to mention about the TLC. Let me introduce. In second year, I don't think you did TLC in your organic chemistry laboratory. So probably it's important that you learn first the theory. So just I will just explain for 5 minutes the TLC, and then we'll continue from here. Let me go back to this Jamboard. Here the frame. Yeah. So so the Jamboard is visible, right? Was that is visible? Yeah.
Yes, sir.
Okay. Okay. Perfect. So the TLC, what is TLC? So as I already mentioned, is nothing but thin layer chromatography. And what's the application? TLC is probably one of the simplest but heavily used chromatography that are especially for organic chemists. So we can't think of our research without TLC. So on average, each research scholar probably uh, do at least 10 to 20 TLCs every day. So that is kind of bread and butter of organic chemistry research. It's very simple. So what's the main principle here? So any chromatography, the main principle, it's like a marathon race. So whenever I explain this thing, I compare this with a marathon race. Why I'm saying so? In marathon race, what's there? So there is a starting point where all the participants starts together at the same time and from the same point. Okay, and there is a final point also there. They suppose whatever distance they have to cover, depend on the race. And when there is a whistle, they starts together. But now all the participants, the mobility of all the participants is not same. Someone champions can move faster. There are some mediocres, they move in a medium rate, and there are some slow people who go slow. Okay, so in the any kind of race, chromatography is exactly the same thing. So chromatography means, so from the name itself, probably you know the history. The chromatography, although it's nowadays heavily used in chemistry, but the pioneer of this was not a chemist, rather was a biologist who used to try to separate the extract of probably leaf or some biological mixture, leaf or flower. I don't remember exactly, but he wanted to give it as a color thing, and then he ran the chromatography, and he actually able to separate those dyes, the colors. He saw nice bands there, so that's why it's a chromatogram. The chromatogram, different band of colors, so from there the name chromatography came. Now the thing is here, the same like in any kind of chromatography. So the main application is to separate out different components. Okay? So any mixture can be a reaction mixture, or can be something we got a mixture of products, or something in a compounds we got from nature or from any other source. Whenever we try to want to separate these compounds, mixture of compounds, then only we use chromatography. And there are so many varieties of chromatography. The simplest one is this thin layer chromatography. There are paper chromatography, there are column chromatography, and nowadays all kind of sophisticated techniques like HPLC. Probably have heard this is high performance liquid chromatography, gas chromatography is there, GC, and so on and so forth. Okay, so let us go back to this TLC thing. So in TLC, it's nothing. It's just needed TLC plate, as I already showed in that video. Yeah, it's a very thin layer. So normally there is a aluminum sheet there. So it's like a so probably you have seen the aluminum wraps. But this is little bit thicker than that aluminum wraps. Aluminum wraps are very it's not, it's very flexible, it's not rigid, but it's little bit thicker. So that's why it's a firm and rigid thing, little plate. And above that, there is a layer of silica, SiO2, with some other components, so that it sticks there on the surface of this aluminum plate. And it's available in a bigger size, like this square boxes. It comes, and as per the requirement, we cut it with a scissor in these small blocks that I have shown in smaller pieces. So after that, whenever you want to do a TLC, now in TLC the thing is, the main utility of TLC is to monitor a reaction. Okay. So monitor a reaction. So how to monitor? In a reaction means what? That is a reactant, there's some reagent, and then you get a product. Okay. And suppose you are doing it for the first time, or you don't know after reacting it for a certain time, 1 hour or 2 hours, whether the reaction is complete or not, or even whether the product is at all formed or not. Okay. So what we'll do, we'll take out little reaction mixture from the little part from the reaction mixture, and then point it on the TLC. So in a typical TLC, we do like this. Whenever you have this plate, this is a silica thing. The ideal thing is you put a pencil mark here, and then you put 3 pencil marks here. Okay. And suppose this is a reaction A, and A to B. From product is from A is the starting material and B is the product. Let's take P. There is the product, and instead of A, is take S. This is the starting material, S, and P is the product. Then it's better. Okay. So in a typical TLC, you have to do like this. You have to put three marks. Okay. So where you take a little bit and of the starting material, you have to dissolve it in a suitable container. Normally a glass vial or a appendix. You take a little bit here and then dissolve with a solution. Yeah, so you will have a solution of S. Okay. Solution of S, and so you take with a capillary. So normally I will show you a capillary. Very thin capillaries are available, glass capillaries. Just dip it here in the solution, and so with the capillary action, little will go inside the capillary, and then you take this capillary, you spot it here. So this will be the spot of S, okay, the starting material. And from the reaction mixture, so this, suppose this is your reaction mixture. You have something, all the reaction thing. So here same, the capillary you will dip here and take it out, and here you spot it. And sometimes it happens, this starting material and products, this mobility is almost similar. It can happen. Actually, in this particular case, Indole case, it happened. So it's better. It's a good practice that you also make a co-spot in a middle. It's called C co-spot, where you take spot this S as well as this P. So why I'm saying so? When there is very close spot, close spots is sometimes is very difficult to differentiate that whether it's a spot for same or different. Okay, so that's why when there is a close spot, it's quite easy. I will show you with the TLC maybe later on. That would be better. Okay, there's a co-spot means spot of starting material, spot of product also. Okay. So after the spotting is complete, you have to transfer this in a this TLC chamber. This chamber is not good. Let us go this side. You need a good chamber. Okay. TLC chambers are typically like these, and here you have to add some solvent. It's called the eluent. Okay, so, and this choice of solvent really depends on the characters of the starting material and product. Okay. So with experience, people will learn this, and sometimes it's also trial and error method. Okay. So normally these are the mixture. The very most common is a mixture of hexane and ethyl acetate. ETOAC, ethyl acetate. This is most common eluent in organic chemistry. In our lab, we 90% time we use this hexane and ethyl acetate mixture of these two. And depending on the character of this compound, the starting material and product, we change the ratio. We change the ratio here and do the thing. Okay, so once this eluent is there, we'll place this TLC thing in here. Okay. So after placing, it will look like this. All right. And this is very important that the mark we have made, no, here it should be some distance should be there. Okay. And this mark, it should not never deep into the solution. It should be up there. Suppose the solvent layer is up to here. Okay. Suppose 1 centimeter. So then this distance from bottom to here must be 1.5 or something like above 1 basically. So otherwise, if it is deep into the solution, then this thing will get dissolved, dissolved, and then it will go here and there. It's very important that this part, the spotting points are above this solvent height. Okay? And only once you dip here, so what will happen? With the again the capillary action will comes into picture. So anything, no, any dry thing, the TLC plate was dry, right? So you put in a solution, what will happen? The silica things will start absorbing the water, the solvents, and with the capillary action, this solvent will start going up. You will see in the video. Okay. So once this solvent will start moving up with the capillary action, then what will happen? It will drag these compounds. S, it will drag S with the solvent. The product will also drag with the solvent. And also in its core spot, it will drag both this solvent, starting material and product. Okay. So now basically the run start. Okay. So you see here. So this is the starting point. So now this is a race between the starting material and product basically. Okay. Who can move faster? So depending on the nature of the compound. Okay. So we are using, there is a silica, right? So silica layer, as I already mentioned. And now some compounds, they binds with silica much better. Silica means what? Silica means Lewis acid. Silica with a S double bond O, right? So this silicon, silica is a very good Lewis acid, which likes lone pair of electrons. Okay. And organic compounds, which is having atoms with lone pair of electrons, like nitrogen, oxygen, this kind of molecules will bind with that silica very strongly. Okay. And once this bind with the silica strongly, then this mobility, the movement will be slow. Okay. But compounds like hydrocarbons, like toluene, benzene, any alkyl chain where there is no only carbon and hydrogen is there, no carbon do not have any lone pair of electron. With this hydrocarbon where there is no heteroatoms like nitrogen, oxygen, phosphorus, these things, those things will not bind with silica that strongly. That will move very faster with the solvent. Okay. So that's why anything it's general term we say like polar and non-polar. Polar means which binds with the silica strongly, and non-polar means which don't bind with silica strongly. So the non-polar thing which don't bind with silica strongly will go up and faster, and the thing which is polar binds with silica strongly will stay at the bottom. Okay. So after this solvent going up, we'll stop the solvent somewhere here. Okay, when it's close to reaching the final point, the top point, somewhere here. Okay. So after this, we'll take this out and dry it up. With just 1 minute in the air, it dries up. Then we'll see inside a UV chamber. The UV lamp is there. We'll just place this silica with the UV chamber. UV chamber also how it looks like. Normally it's a box. So this is the thing with 3 spots we have made. So there ideally the situation is, we suppose in this particular case, the starting material is more polar, suppose. Okay, we are assuming. So the TLC will look like this. Okay, so the starting material is more polar. so it moved up to here. Product is less polar, so it's ideally will go up there, okay, upper than S. Hmm. And this co-spot, so there you can, the co-spot, you will say one spot here and one spot here. So because both we spotted here, it's a piece. So if you get a TLC like this, that means it's a fantastic reaction takes place, where there is in this reaction mixture, there is no spot here with the correspond to the starting material. That means all the starting material got consumed, okay, and exclusively the product is formed. Okay. But in many cases, you can see that some amount of maybe like this, something is like this can also happen. So that means some amount of starting material is still left, okay. And from the intensity in the UV, you can also somehow guess little bit whether how much actual conversion happened, 10%, 20%, or 80%, like this. Although this UV color, we should not judge on this because some compounds can take a lot of absorb UV and can see brighter even at a lower concentration. But just to have a rough idea, we can also sometimes use this TLC thing. But main thing is to monitor the reaction, whether the reaction is complete or incomplete. Like this, okay? So this is the basic thing. We'll now go back to the video and we'll see how really we have done this.
For solution, we are going to spot here. So A is acetophenol, EH is the.
But here in this particular case, you know, in previously I've taken only one starting material, but in this case, we had already in the two starting material, acetophenol and phenyl hydrazine, and in between also we got something that a hydrazone, and then we did that reaction. So it is little bit complicated. So previous case only 3 spot was good enough, but you know, in this case two starting material, one intermediate step, and then one final step, and one co-spot. That's why there are 5 spots we have made. Okay?
Phenyl hydrazine, and P here is the product mixture where we expect the product, and this H is the intermediate step, that phenyl hydrazone, and C is the co-spot, which is the mixture of all these 4 steps. You spot it here using this capillary here, this glass capillary, you can see, and this is some solution of ethyl acetate just to wash this glass capillary. All right, so I'll ask Nidhi to spot all these things here, and during the run I will show you. You need to insert this glass capillary inside the solution, just touch it, and through the capillary action some amount of solution will come out, and then you need to spot that one in the required position here. Yeah, show it again. Yeah, in that spot. Yeah, just touch it. So that little amount should go there. It should not be too much, should not be too less. It's just the optimum amount that comes from the experience. Just for your knowledge, to put optimum amount so that the circle should not be too high amount. It should be a decent kind of 1 to 1.5 millimeter of circle solution. Yeah, we continue this the same thing for the other solution as well. So now we'll put the TLC.
All the spotting is complete now, so we are inserting into the TLC chamber.
Let the TLC chamber carefully, and you see only little part of it will be inside the solution here. The so up to here is there is a pencil mark.
You see there, that solvent font, the solution is lower than that the pencil mark, okay, and then once you insert, immediately that solvent will start growing up with the capillary action. So whatever we are seeing here, actually it goes up with the capillary action, okay. The real solvent level is below this P, up to the bottom point of this middle P, up to there is a solvent actually. Whatever we are seeing going up is due to the capillary action.
And we have made all the spots there, and the solution, the eluent should not, this mark, pencil mark should not go inside into the solution. Okay? So only through the capillary action, solution should go up. You can see already this is moving up. All right, and once this solution is moving up, it's taking all these compounds, and depending on the polarity, some will move faster upward direction, some will move slower, and there should be some difference in this RF value. All right, we'll continue this TLC until the solution goes up to a certain level. and then it will take it out and then see with the in the UV chamber.
Hmm.
Run is complete. Now, then we'll heat the UV chamber. Yeah. Maybe too bright. Yeah. Now the spots are visible. You can see here the first one, as I said, is acetophenone spot. Second one is the phenyl hydrazine. This is our product spot. This fourth one is for the phenyl hydrazone, and this is the co-spot. Okay?
You can see in this point, let me explain. You can see my mouse, I guess. So phenyl hydrazone is the most polar because there are two nitrogens, and both the nitrogens are sp3 hybridized. So that's why the lone pair is pretty much available to react or not react, bind with the silica. That's why it's almost staying in the bottom. It's not really moving up. Okay. And this acetophenone is relatively less polar. So I mean, among all this is the least polar basically, because only one oxygen is there, and oxygen is not a that good donor compared to nitrogen. So that's why it's this is it's traveled the most distance. Okay. The product here, the first of the product here. The product here, there is one nitrogen. Nitrogen is a better donor of electron, right? Because it's less electronegative compared to oxygen. But in the indole case, the lone pair of nitrogen is involved in aromaticity. Okay. So that's why it's okay. It's a donor, but it's not super donor, because other if you donate with silica, then the aromaticity will get break, right? So that's why it's an in between case. So that's why compared to acetophenone, it's a little bit less polar. Yeah, but it's sorry, compared to acetophenone, it's more polar here. But compared to phenyl hydrazine, the other starting material is definitely less polar. And so that's why it comes here, the one starting material number one, starting material number two, and this is the product. And another thing you see, we got a very beautiful reaction. Only product is there, and there is no starting, no phenyl hydrazine is there, and as well as no acetophenone. No? So if you just extend the line, the acetophenone spot should come here, and this is the product spot little bit below. But one thing is, the gap is not that much, not that much. So that's why the utility is sometimes even it comes even closer. Okay, the difference, because the mobility, the movement rate is very close. Sometimes it becomes very closer. So that's why this core spot sometimes very helpful. That's why I'm saying so. So when there is suppose this is here, so you extend the line like this, you are not sure that whether okay, I'm extending the line properly, it may be like this or like this. But once you put a core spot, even if those are very close, you can see a 8 kind of thing. You see, like an 8, very close, although, but this 8 kind of thing will come. So that means you will be sure that no, there are 2 spots are there. Okay. 2 spots are there. It's not a single spot. It is 2 spots, and the reaction happened, and then starting material and product both are there. So from the experience, you can learn more. But another trick is we can increase this distance between these two. Just run it for one more time. Okay. So one round of running we have done. So we can take the same plate and run for one more time. So after a second time running, the difference, suppose after first run, the difference is like this. Okay, after second run, you will see the difference becomes higher. Then it's much more easier to differentiate. That is what we have done here. We ran it for second time.
Also, you can see already from here. So the color of the product is much more brighter than this acetophenone. Although these acetophenone spot and product spot, these are quite close to each other. The RF value difference is not much. The second spot, this phenyl hydrazine, is very polar because of the hydrogen, nitrogens, presence of the 2 nitrogens, and those are strongly binding with silica, so it's very polar. Acetophenone and the product is quite close. Okay. And this hydrazone spot here, it's got hydrolyzed in silica, that's why it's mainly showing the spot of acetophenone. the core spot, but the core spot you can see already. This is already two spots we can see. So in core spot, what we have, the acetoquinone we have as well as the product. We can see like an 8 here. That means there are, although those two are close, but there are two separate spots. And our product spot, you can see it's very nice round spot, and the product is formed, right? So to have a better understanding or better separation, rather we'll run it again once more, and then we'll show you that. I have ran it for one more time. Now you can see the difference is a little bit more here. So basically, this is the product spot here. Okay. And I've just taken the TLC in a horizontal position so that you can see it better. This is the product spot, and this is the acetophenone. Okay. This is the reactant acetophenone. Other reactant is here, the base. And you can see if you extrapolate, the position of the product is here. Okay, and then I mean the RF value from the distance from here to here, and this is the acetophenone. So definitely the product is little bit more polar than the our reactant, but the difference is not too much, but it's quite understandable. So these are the thing here from the TLC from the lab. Now we took that product, it's quite pure, and and we have done the other spectroscopy analysis.
All right, so this is from the video part. Just one thing to before I conclude. Many times I have mentioned this thing, no, this RF value, RF value. What is RF value? RF value is nothing but this thing. Suppose let's take this TLC itself. Okay. Better to draw a better TLC. We already have this TLC. We can show it here. Suppose this is the starting point. Okay, and after this running is complete, suppose we run this one, the solvent ran up to here. After running is complete, there's a pencil mark already there, right? After the running is complete, we'll make another pencil mark here. So now this is the distance from starting point, and this is the end point for the solvent. Okay? Now the thing is, let us take this one. Suppose the S is here, ideal case. So the acetophenone case, which we have seen this. No, the acetophenone is here, and product is little bit below. Sorry, product is here, below here. This is post spot. For RF value calculation, this starting material and product, these two are important. So RF value is nothing but this thing. So this distance will measure with a scale, okay? And we will take this as one unit, one. So from this pencil mark to this pencil mark, we'll take as one. Okay? And compared to this, whatever distance is there, we'll calculate. Suppose in this case, we are taking maybe if this distance is 1, it will come maybe roughly I'm telling 0.8. Okay? And this distance for product, suppose roughly it will come 0.5. Okay? So we'll say the RF value of the starting material, it's called RF. RF value of starting material is 0.8. RF value for the product is 0.5, like this. Okay, this is called the RF value. All right, so I will go back there. Although it took little longer today, but I believe that you learned something new. Okay, Devasita, what do you think?
Yeah, so thank you, Ramon, for discussing in detail the TLC. Though I think the students have done this in their second year. So there in second year lab there is a details on TLC. Anyway, so this is a very good reminder for them. And for students, I always want that you should ask question, but you are always new, and that's why sometimes we don't realize whether you understand everything or not. Anyway, so at the last part, again, I am sharing the spectra, and okay. Yes. So we got our product. So we have already done the thin layer chromatography. We have checked that the compound has formed very nicely. And now we will do the analysis of the compound, synthesize compound using different spectroscopic techniques. So we'll use the UV visual spectroscopy. The UV visual spectra is like that. So what you have to write, you have to write the transition which is responsible for the UV visual spectra. And then this is the FTIR spectra. Also, here the values are there, so you have to write what is responsible for what in FTIR spectra, and here is the NMR spectra of the compound. As there is no aliphatic proton, so it's only aromatic proton, so it's condensed in that aromatic region here. So you have to write this one. So please submit your data before next
Just I
day.
think it's a carbon spectra. Right? Yeah.
Oh, yeah. This is the carbon spectra. Yes. Okay, so I'll provide a one HNMO spectra. Yeah. Sorry, this is carbon spectra. Sorry for the mistake. Okay, and before the next day, next week you have an exam, so there is no class, so you can submit this work before next experiment. Okay, and previously I have mentioned that you have to choose one project for your one, and the project will start once the two more experiments are left. So two more experiments is over, but you can choose your project and start working on that. And if you have any question.
Madhur is asking the workup step. How does rectified spirit help to remove the acetophenone? Because it dissolves it.
Okay, so actually acetophenone is highly soluble in cold spirit, but our product, the hydrazine, is not soluble in cold spirit. So at the end, so if you wash with cold rectified spirit, the excess of acetophenone will dissolve in cold rectified spirit and will go off.
Hmm.
Yeah, so if there are no more questions, so thank you very much and have a nice lunch.
Yeah. Also, wish you all the best for the next time.
Yeah.
Okay then.
Okay. Bye.
Stopping the video.